Hey guys, it's Mrs. A. Hope y'all are doing great. I miss going up there and seeing y'all every single day. Apparently, I have a hard time sitting at home doing nothing. So I put together this little video because I know some of y'all are having a hard time with this heat chapter. This is actually a really easy chapter. You're always trying to find the delta H. The delta H means how much energy was given off. So you can figure out if a reaction is going to be hot or cold by determining the delta H. All right, so there's a couple of ways we can do this. The very first thing that you need to know is your phase diagram. These were the really easy ones that we did the very first day, where it looked like this. Oh, hold on. I promise these videos will get better. All right, so this was your solid, this was your liquid, and this was your gas. And so you could determine at what temperature you were going to have the different phase changes. So like right here, this was always at the same temperature because this axis was temperature and this was time. And so the temperature stayed the same, which showed that right here you would go between a solid to a liquid or a liquid to a solid. So this would be like your heat of formation. It could also be your melting point. It could also be your freezing point. So right here, at this particular temperature, half of your substance is melting, half of it is freezing. Same way right here. This is at the same temperature. Half of your substance is going from a liquid to a gas, half of it's going from a gas back to a liquid at this one particular temperature. So those were your phase diagrams. Every time you have an increase, though, you know you have a different state of matter, a solid, a liquid, or a gas. The potential energy diagrams. There are several things that you can determine from your potential energy diagram. One of those is to calculate your delta H, which was your products minus reactants. So they could look like this, or they could look like this. All right, so this would be your reactants. This would be your product. Reactants, product. All right, so this would be the amount of energy. So I'm just going to write joules right here for energy. And this would be time. So this would be the time that it would take for your reaction to actually occur. So this shows how much energy you have in your reactants. It shows you how much energy you have in your products. So if you look at this one in particular, I have less energy in the products than what I started off with, which law of conservation of energy says you cannot create or destroy matter. You can only change it from one form to another. And so look, I had to do something with my energy. I have less energy right here than when I started off with, so that means I lost that energy in the form of heat to the surroundings. So this reaction is called the system, and you just lost energy to the surroundings. If I want to figure out exactly how much energy, I can figure out, okay, how much energy did I have in my products? How much energy did you have in your reactants? And you can do delta H is equal to products minus reactants. So for this particular graph, I'm going to be releasing energy. So this is an exothermic. It's going to release energy to the environment. It's going to feel hot. When you have an exothermic reaction, your delta H, whenever I have less energy in my products than what I started off with, your delta H is always going to be negative. It shows that you have less energy right here than what you started off with. I look at this one, I have more energy in the products than what I start off with. So the only way that would be possible is to gain energy. So if it gained energy from the surroundings, that is an endothermic reaction. Your delta H, whenever you do your products minus reactants, would always be positive. So just by looking at your delta H's, you can determine whether it's going to be a hot reaction or if it's going to feel cold. Exos always feel hot, endos always feel cold. So that's the whole reason why we do this. So, I mean, there's several things that you can determine. Exactly what was my delta H? Was it an endothermic or was it an exothermic reaction? Okay, your activation energy. Your activation energy is how much energy it takes for your reactants to break apart. So your activation energy is from the bottom of the reactants to the top of the hump. So from the bottom of the reactants to the top of the hump. So if you look, the activation energy on the exothermic is always going to be a lot smaller. That's why exothermics are more common, more frequently found in nature, because it has less energy to break the reactants apart. This requires more energy. Now, one of the ways that we can lower the activation energy is by using a catalyst or a biological enzyme. So I can actually add a catalyst to this, and by adding a catalyst, my energy of the reactants and the energy in the product stays the same, but it's going to lower the size of the hump. So you can figure out exactly how much activation energy it's going to require. So let's start talking about this right here. Again, you're going to calculate the delta H. So this is calculating delta H, and so is this. You're going to do it the same exact way, do products minus reactants, but you have to look up the values for the products and the values for the reactants in a table form. The next thing you need to know for your test is Q is equal to MC delta T. This is trying to figure out how much energy was gained or lost if I know the mass of the substance, specific key of the substance, and your temperature change, last minus first. With a calorimeter, you're doing the same thing, your MCAT equation, but this one you have to do twice. Once to figure out how much energy the water and the calorimeter gained, because that's going to be equal to the amount of energy that the substance that was burning lost. So this is all the stuff that the regular needs to know for their test. Pre-AP needs to know this also, but in addition, pre-AP also needs to know their heat stoic and Hess's law. So let's take a look at the review that was given out to y'all. Okay, so right here, you had to figure out by circling which part of the sentence which word made the sentence true. In an exothermic reaction, what happened? Is heat absorbed or is heat lost? Now, I want to look down at this next little part. They actually gave you an energy diagram. If I look, this is the reactants, this is the product. The product has more energy than what we started off with. That means it had to gain energy from the surroundings. So if it gains energy from the surroundings, it's going to feel cold because the surroundings are going to have an absence of heat. So this is going to feel cold. It is an endothermic reaction. If I did products minus reactants to determine the delta H, it'd be 100 minus 50, which would give you a delta H of 50. It's positive, so that tells you with it being positive, it's an endothermic reaction. If I want to figure out the activation energy, I go from the reactants to the top of the hump. So it'd be from 50 to 250. So there's 200 kilojoules of activation energy. You're going to do the same thing over here for your other reaction. Look, I've got less energy than what I started off with. That means the energy had to be lost to the surroundings in the form of heat. Okay, so on this bottom part, you're going to be asked to figure out if it's endothermic or exothermic. So if the energy is a reactant, that means that you gained energy, which is endothermic. If the energy is a product, that means the energy was released to the surroundings, calling it exothermic. So if I look right here on question number 3, the energy is a product. That means you had to release this energy. It's going to be released in the form of heat. So this would be an exothermic reaction. If you look down here at number 5, the energy is listed as a reactant. That means it had to be absorbed in, just like right here, in order for it to make the reaction occur, calling it an endothermic reaction. So this would be exo because I am releasing heat as a product. This would be endo because I am absorbing it in. Okay. And then burning a match. A match is going to feel hot because it's releasing energy to the surroundings, so it would therefore be an exothermic reaction. Okay, on the next page, you're talking about your different potential energy diagrams. So if I look right here, these are the reactants. This is the product. All right, so to figure out your delta H, you would do products minus reactants. So 100 minus 50 would give you 50. It's a positive 50, so this tells you that it is endothermic because it had to absorb energy in order for this to occur. So therefore the surroundings are going to feel cold because of an absence of heat. All right, to figure activation energy, you go from the reactants to the top of the hump. So 250 minus 50 would be activation energy of 200, because that's a lot of activation energy. These do not occur as frequently in nature because of that huge activation energy. This would be an exothermic reaction. If you look, the hump is a little bit smaller. Now you can add that catalyst in to decrease the activation energy, which would make the reaction occur a little bit faster. Okay, so the next portion we're going to talk about is how to calculate your delta H by looking at a graph or a table. And so this is the reaction that you're going to find. Here are your reactants, here are your products. And so just like the potential energy diagrams that look like this, where you do your delta H, you can calculate your own energy in your reactants and energy in your products by looking at this little table off to the right. So we're going to say products minus reactants. Well, if you look, I've got 1 carbon dioxide. So I'm going to look at the table, and it tells me that carbon dioxide has a negative 393.5. So I'm going to say negative 393.5. I have 2 waters. I'm going to come over here, and the energy in water is negative 241.8. I'm going to multiply that by 2. Whenever I add those together, it's going to tell me how much energy I have in the products. Then I've got to figure out how much energy I have in the reactants. Well, look, I've got CH4 plus O2, because O2, that's an element. Elements do not have bonds, so therefore there's not any energy within those bonds. So anytime you see an element, you know that the energy is going to be 0 because there's nothing holding the element together. So really, I just have to see in there, it shows it right there, 0 energy into all these elements. So CH4 has a negative 74.8. I only have one of those, so it's negative 74.8. Whenever I calculate that, simplify it, I just multiplied that by 2, and that way I can figure out how much energy was in my, how much energy I had in my products, how much energy I had in my reactants. Guys, like whenever you have a minus a negative number, those are both going to turn into positives. So therefore, you had a total energy change of negative 802.3. Negative 802.3 kilojoules. Now, that's a negative, and so we had just talked about with the potential energy diagrams what happens if you have a negative delta H. So that would be the same thing as if I would have drawn it off over here to the side, just like this, and I would have said the reactants would have had energy of 74.8. The products would have had an energy of negative 877.1. And therefore, when you subtracted them, it would have told you what that energy change was right here. Okay, for the next section, you're going to be talking about calorimetry. So you're going to use Q is equal to MC delta T. So for the first little bit, it tells you like your mass of your copper, your temperature change of your copper. It tells you specific heat. You're just plugging and chugging. So mass, specific heat, temperature change. Remember, temperature change needs to be last minus first. Okay, so when it gets a little bit further down here, you have to, for these equations down here, you're going to be putting something inside water. So remember, Q loss is equal to Q gain. So I want to figure out how much energy the water gained by figuring out the mass of the water. Specific heat of water is always 4.184, and your temperature change of your water, to figure out how much energy the water itself was going to gain. If I know how much energy the water gained, I also therefore know how much energy the metal lost. All you have to do is change your sign. But it's going to be the same amount of energy because there was only one place where the energy had come from. So if that's how much energy the water gained, you therefore know that's how much energy the water lost. On the next one, okay, so the very last part of this right here, or this review, you're going to use MCAT 2 different times. Once to figure out how much energy the water gained, to figure out how much energy the substance lost. And so like right here, you're going to figure out how much energy the 2,000 grams of water lost. And by using this equation, 2,000 grams, here's a specific heat of water, there's your temperature change of the water. Figure out how much energy the water lost, so you can figure out how much energy this water gained. All you have to do is change your sign. You can do the same thing right here. You're going to find the Q of your water to figure out how much energy the water gained, because that's the same amount of energy that the chromium lost. And then you can solve for the specific heat. Now, regular can go ahead and stop right here. There's one more topic I have to go through with the pre-AP, and it is over Hess's law. So with Hess's law, you're going to be given one reaction, like right here on the very top. Basically, you're going to manipulate this reaction by using these three other subsidiary reactions. Because sometimes I can go directly to these products. Sometimes I've got to do other reactions to get to the products. So I can manipulate this to where if I know what energy these three reactions are given off, I can calculate how much energy the top reaction should give off without having to actually go into the lab. All right, so it's really easy. You're going to find, I always try to do like oxygen and carbon and water last if possible. So this is an oddball one. NH3 is only found right here. I need it to be a reactant. It's listed as a product. So therefore, I need to flip this reaction to write this right here as a reactant. So when you rewrite it, just like right down here, as NH3 a reactant, I can go ahead and scratch this one off. What I do is I took that negative 91.8, and you have to flip the sign also, because whatever you do to the reaction, you also have to do to your delta H. Now, it's in the right spots, but I needed 4 NH3, I only have 2. So I want to multiply this entire thing by 2. So now I will have 4 NH3s, 2 N2s, and 6 waters. So when I do that, I need to multiply this by 2. All right, so now what I like to do is I like to go ahead and box it in. So I have 4 NH3s on the left. I now have 4 NH3s on the right. That reaction is stuck in place. I cannot change it again. Okay, so like I told you, I like to leave oxygen for last. Let's look at NO. NO is found right here. It is a product. It's a product. It's where it needs to be, but I need 4. I only have 2. So therefore, I need to multiply everything here by 2. So 2, 2, and make this a 4. That means I need to multiply my delta H by 2. So now that I've got 4 NOs and I've got 4 NOs, I can go ahead and box them in. I need 6 waters. Now the only place water is found is going to be right here. I need it as a product. It is as a product. And so now I just need to multiply this right here. I need 6 of them. So let's multiply everything right here by 3. So this would be 6 times 2. 3 times 2 would be 6. This would be 3. 3 times 2 would be 6. So go ahead and box that in. 6 waters. 6 waters. Okay. Now we're in here, did we talk about nitrogen? And so, look, nitrogen's on the left, nitrogen's on the right. Just like in math, if I have something on each side of the arrow, it can cancel out. So 2 nitrogens, 2 nitrogens. If I look, I've got 6 hydrogens, 6 hydrogens. They can cancel each other out because they're on opposite sides of the arrow. I needed 5 oxygens. Well, there's 2 plus 3 is going to give me 5 oxygens, which is what I needed. So let's go ahead and box those in. Now look, everything's either boxed in or canceled out. So therefore, you know you have every same amount of everything that you need, and it's on the proper sides of the arrow. So now I can go ahead and just add up this delta H, and it would tell me what my final product is. If I multiply that by 2 and multiply this by 2. Oh, you know what? I forgot to write this down. I multiplied everything here by 3. So I need to multiply this by 3. And if I do that and I add it all up, my delta H for this would be negative 1,628 All right, so your total energy change would be negative 1,628.2 kilojoules. With it being negative, it tells you that's going to be an exothermic reaction. And this is as hard as it gets, guys. You just have to manipulate those equations by flipping it. Make sure you box in. That kind of helps you figure out where things are at, so you know not to change this equation once you have something boxed into it. You'll have a test coming up on Monday. And hopefully I will see y'all soon. If you have any other questions, let me know. Send me a message on Remind. All right, you have a great day. All right, bye.